Well, looks like we can get started, folks. Welcome back. It'd be nice to have more students, but if it's just us three, we'll get through it one way or another. Don't know where everyone else has been, but maybe it's something I said. Who knows? We'll get through it one way or another. Any questions at all, though, to start us out? Okay, well, with where we're at so far, we're going to have our third exam next Tuesday, but we're constraining it just to those sections since I feel like sections 5.1, 5.2, 5.3, we're so new with that content, throwing it on an exam doesn't really make sense at the moment. This will be content that we'll see on the final exam. And after we move through section 5.3, diagonalization, we'll be heading over to chapter 6 on looking into the geometry of vector spaces. So that's where we're at so far. Any questions or comments at the moment? Okay, well, you kind of probably expect the pattern to be just the same. Exam 1, exam 2, exam 3 run exactly the same. The formula sheet for this exam will involve invertible matrix theorem, definition for a basis, and definition for having a subspace. So this will be the provided sheet. And sure, it's just three different things here, but that's really one big, huge theorem that orients a lot of stuff. The other thing you can expect on the real exam 3 is that it's also written very similar to exams 1 and 2. It's going to be 20 questions in total. A lot of them will be concept questions. Some of them will require some computation, but there won't be too many really long questions. Then after that, on this week will be a normal week. Let's see here. Will it be April 22 to April 28? It'll be kind of a normal week. We'll have a normal day on the 23rd, so we'll be looking into new content. But then on the 25th, we could look into new content, but I think just talking about the final exam is what makes the most sense. So we will be reviewing on that day right there. That means we might not make a lot of headway into chapter 6. Our opportunity would be on whatever content we look into on the 18th after the third exam, and whatever content we get to on the 23rd. So it's a decent headway into chapter 6. Looks like we lost some days due to snow days and stuff like that. I think I took a sick day in there somewhere. So that's where our course is going to end, just a little bit into chapter 6. What I will do, though, is for folks that want to read a little bit further into chapter 6, if you have a lot of free time and you're just bored, you do go a couple sections further into there. I'm going to include some extra credit questions on the real final exam involving those. So they'll be low stakes, so you don't have to get into those. But for people who have the time and energy, there will be a reward in getting a little bit further. I will post the rest of my notes just to assist in that kind of endeavor. But I think that's my major announcements at the moment. Let me see if I can bring this back. There we go. Any questions at all then before we get started? Okay, well, here we go. We're now back to this definition. Let's take a look at it just as a warm-up. The thing to recall from section 5.1 was that it's majorly about getting to know this right here. If you have a matrix equation where multiplying 8 times x is just rescaling x by lambda, and critically, x is not the zero vector. If it was the zero vector, you could put any number right here. You lose the concept of an eigenvalue if there's a 0 where the blue x is. But if this holds, then we'll say lambda is the eigenvalue for that matrix A, and x is an associated eigenvector. In section 5.1, all we did was introduce that definition. We showed how to find eigenvectors when you know you have an eigenvalue, but we never actually showed how to find eigenvalues at all. They were just supplied, and we were asked to determine if it's an eigenvalue or not. So that's why in section 5.2, this section is a little bit more pivotal. We're looking into the characteristic equation, and now from this equation here, you'll recall that's what we used to test if we had an eigenvalue. An eigenvalue meant A minus lambda I has non-trivial solutions. In other words, the determinant is 0. So if that's the equation you use to test if you have an eigenvalue or not, by plugging an eigenvalue here, it means you could also use that equation to just find the eigenvalues. And that's exactly what we'll be doing. So this generates eigenvalues. The book talks about the characteristic polynomial a lot, making it sound like something new. But all that's happening on the characteristic polynomial is you're looking at the determinant A minus lambda I. It doesn't have the equal 0 part. So whether you're talking about the characteristic equation, the characteristic polynomial, you're really talking about the same kind of stuff. The determinant of A minus lambda I just keeps on coming back over and over again. Related concept? is that when you write out this equation, it becomes a degree n polynomial in the variable lambda. Fundamental theorem of algebra tells you you can always solve that equation no matter what. Sometimes your solutions could be complex valued, so there's that downside. We'll see it happen ourselves. And now the related theorem, this is one we used to test if we had eigenvalue, told us that lambda is an eigenvalue if and only if it satisfies that characteristic equation up there. So from all that work, in part A, we'll find the eigenvalues of A and state their multiplicities. And this is pretty much how it goes. After doing all of our work in linear algebra, sure, this is all new definitions, but you'll notice everything just sort of fits in like a Jenga tower with everything we've done before. So if you want to do determinant, A minus lambda I, this just means you're multiplying the n by n identity matrix by lambda. You have lambda across the main diagonal. And so that means you're subtracting lambda from all of these entries here on that main diagonal. So the determinant takes on this form. Right where we have highlighted, we'll go whatever the scalar is, reduced by lambda. Then same values elsewhere. So that's our column 1. In column 2, we'll go 0, 1 minus lambda, 0, 0. Column 3 will be 0, 5, 2 minus lambda, 0. And here's our last column, 0, negative 10, 0, and 3 minus lambda. So that's our determinant to work with. It has some nasty features about it. We might notice that from chapter 3, section 2, there's some wonderful theorems that helps you combine row reduction with calculating this determinant, but that's almost never done in this context. And the reason is, if you do any row replacement operation whatsoever, what will happen is you'll be taking these things that involve in variable lambda, and you're just putting it into more and more locations. You make your determinants more complicated with row reduction operations most of the time. Because of that, we just have to compute usually what we're looking at. So let's hit it. I wouldn't want to go this way. A cofactor determination down column 1 is going to be a nasty way to go, because now you have 1, 2, 3, 3 by 3 determinants to settle. So instead, we'll go this way. Across row 1 is just going to involve 1 3 by 3 determinant multiplied by this scalar right here. So that's going to be our cofactor expansion. We have a 1 minus lambda multiplying this reduced size. Let's delete this row 1, this column 1, just to visualize it. And this is what's left behind. 1 minus lambda, 0, 0. Going column wise. 5, 2 minus lambda, 0. Negative 10, 0. 3 minus lambda. So we're getting there. That's an easier determinant to calculate. Still, depending on how you decide to calculate it, it could be a lot of work. Any suggestions on the best way to compute? Going, say, down this column, maybe? That would work for this one, absolutely. But one thing to also notice is that we were kind of stuck with a not great matrix on this one, because when we look at the main diagonal, it was neither lower triangular nor upper triangular. There's entries above and below that are non-zero, but this is a better situation. On this matrix, this one would be considered to be upper triangular. It's been a while since we've done determinants, so you might not have had that thought. Exactly. We can go and multiply all these values right here, and we're going to get the answer. But keep in mind how familiar that might feel. Main diagonals are suddenly like the most important thing if you're doing a determinant, or just for a refresh on this one, if you're looking for eigenvalues and you have a triangular matrix, your eigenvalues are also just exhibited right here across the main diagonal. That's interesting because the determinant is the product of these entries. So it sounds like your determinant could be your product of eigenvalues. That's a really interesting concept. And it turns out to be true. We'll have a theorem supporting it. So next step on this one, we will take 1 minus lambda It'll multiply this one, so we could just bump the power. It's now being squared. Multiplied by 2 minus lambda, multiplied by 3 minus lambda. And this is what would be referred to as the characteristic polynomial. The author asks for it, but I'm not as worried about it as I am about the characteristic equation. Now it's a characteristic equation. We set it equal to 0. We're looking at this thing right above. Either way you view it, you're doing the same thing. You're looking for the eigenvalues. And this is nice. It's in a fully factored form, so we can just state them right here. I'll list them out in order for our first eigenvalue. It's lambda 1 equals 1, but interesting concept with this is it has an algebraic multiplicity of 2 because it came from a factor with a power 2. So I'll write here, multiplicity 2. You don't have to say this, but it's actually relevant to section 5.3, so it's a best practice if you notice a higher multiplicity. The next two are going to be lambda 2 is 2, and lambda 3 equals 3. I should say this is a coincidence. My subscripts match up with the actual eigenvalues themselves. That could have came in any order. But we did it, folks. It said find all eigenvalues, and this is what it amounts to. Now, 4x4 matrices, to get eigenvalues this easily, this was a really, really rigged problem. I put zeros all over the place just so that we can get to the determinant easily. And if we couldn't get to it that easily, you might notice finding eigenvalues, it can be pretty hard. But this one's done. And what we'll do next is find the eigenspace that corresponds to the eigenvalue, lambda 1 equals 1. We'll also hide example 2. I think we need more pages on this than I realized. But any questions, folks, on that first step of producing the eigenvalues? Okay, so that's kind of nice in a way. You're just reusing this equation, determinant A minus lambda I, reusing chapter 3 to calculate the determinant, and then your training from algebra will get you to the right solutions. To get the eigenspace, we have to do something pretty similar, but now we're doing row reduction. The eigenspace is going to contain all possible eigenvectors, and it means we're going to solve A minus, I would put lambda here, but we have a specific one, so let's put in 1 times I x set to the 0 vector. Solving that equation there, we're looking for the null space of A minus lambda I, where lambda is 1. And so, well, that's, again, a chapter 1 problem. That's kind of cool in a way. If you nail chapter 1 really well, then everything sort of comes back to that. Well, chapters 1, 2, and 3, I guess. Everything is a source from that material. This will have an augmented matrix that goes, let's grab this just so we can see it. Same thing as we did before. If it says minus lambda I, it just means you're subtracting 1 from this main diagonal. And so this would come out as a 0, 0, 1, 1. Column 2 is going to be 0, 0, 0. That's kind of nice. 4 zeros. I think I only said 3 of them. Column 3 will be 0, 5, 1, 0. And last column, 0, negative 10, 0, 2. Then it is also augmented by this right-hand side, the 0 vector. So let's throw in our indication. And now that's the matrix we'd like to reduce and fully solve. Any questions, folks, on getting to that step? Okay, kind of the nice thing about chapter 3 is when you get used to A minus lambda I, you'll notice you're just reusing these ideas and computing through that over and over again. So it becomes pretty familiar shortly. Let me get this out of the way. We've got our right matrix. And also, because lambda 1 equals 1 is an eigenvalue, usually the row reduction and these kinds of things goes pretty fast. Let's see here. We just have to decide how we want to row reduce. Maybe we can make this row 3 or row 1 go 1, 0, 1, 0, 0. Multiple great ways to do this, but I guess I'll go that route. Column 4 can be column 2, 1, 0, 0, 2, 0. And what do we have left? This will, I guess, be our third row. 0, 0. And let's divide by 5. Why not? 1, -2, 0. This is an entirely zero row on row 1. So all zeros now for row 2. And what have I done here? Let's see. I don't really like my rows, but I'll keep them the way they are. I think a better way would have been to swap row 2, row 3. That'd get it in an echelon form maybe a little bit quicker. Or will it? Well, let's see what happens. Let's keep on row reducing. We're going to take row 1, multiply it by -1, add to the row below, and this will give us a 0, 0, -1 on this location, 2 and 0. Then row 3 goes 0, 0, 1, -2, 0. I guess we're okay the way the rows were entered in. Then 0, 0, 0, 0, 0, lots of zeros, but that's the goal in linear algebra, to produce many zeros in your matrix. And we're just about to our echelon form. Let's copy in rows 1 and 2 as they are. Well, I said as they are, but we're going for reduced row echelon form. That means, let me take a look. That wasn't quite the right approach, was it? We need to take this as a pivot point, eliminate the entry above and below. So let me backtrack on my row reduction. Must not have drank enough coffee today. Let's make this happen. I'm going to take this row 2, put it in, but also multiply it by -1. So 0, 0, 1, -2 and 0. That looks a little bit better. Now, with this row just as it is, you can combine multiple operations. Let's also add this row up to row 1, replacing it. We will get a 1, 0, 0, 2, and a 0. Next, let's take this row 2 just as it is, add to the row below. That wipes everything out, so it's all zeros below. 1, 2, 3, 4, 5. 5 more. And provided it didn't make any weird mistakes, this looks like it's in our reduced row echelon form. Well, any questions, folks, to that stage? Okay, now looking at the instructions a little bit closer, maybe we didn't even have to get that far. Echelon form might have been just fine on this, because let's look at what we were doing. I'm writing it down the process where you're finding the eigenspace. You might start saying x1 equals, x2 equals, getting into parametric vector form and all that. But no, all we wanted was the dimension. And there are some great results along these lines. This is a null space, and the dimension of a null space is equal to the number of free variables that you see in the system. Let's take out that theorem just to exhibit it. And let's paste it in here, since that's a really important concept. That must have came from section 4.5. We're talking about dimension. This is our one-stop shop for it. And where is our good theorem? It's somewhere in here. This is the one. It says the dimension of the null space is the number of free variables. It means we could have been okay with echelon form. We see the number of free variables in that format. This will be a good screenshot for us. Let's just dump it in here. So we're looking at a null space because we set this equal to a 0 vector. And looking at this again, we have a free variable here and a free variable here. So x2, x4 are free. It wants the dimension of the eigenspace corresponding to lambda equals 1. And so we can say, therefore, the dimension is 2. Since there are 2 free variables. Well, we did it, folks. We found the dimension of this eigenspace is 2, and we found above the algebraic multiplicity of lambda 1 was also 2. This turns out to be a little bit special, so let's maybe just add a couple words here. This is sometimes thought of as the algebraic. multiplicity. And this dimension is sometimes thought as the geometric multiplicity. And it's nice that these come out exactly as 2. If this was a 1, then we would have said that the original matrix A is defective, which is it sounds like an insult. It sounds like you're saying something terrible about that matrix. And what it really means down the line is you cannot diagonalize it. Any kind of work, if this is an applied problem in a physical setting, any work on that matrix A is going to take potentially a lot more additional work. So this observation here and here is really all about what's going to go down in section 5.3 when we try to factor matrices by diagonalizing them. But so far, this is where the concepts ends on this one. Any questions at all, folks, on this problem here? Okay, well, one down. Let's see what we're getting into next. So that's a good theorem to come back to. This is pretty much everywhere now that we've looked into dimensions. Null spaces comes up anytime you're looking into eigenvectors. And our example 2 is, well, different kind of problem. All it wants is the eigenvalues of A. Oh, and I'm throwing stuff. Let me grab that. If we want the eigenvalues, then all we're really going to do is take a look at determinant A minus lambda I. Once we compute this and get the characteristic polynomial in a nice format, we'll set it to 0 and solve. So it's kind of a nice little warm-up problem here. Let me zoom in a bit. Determinant A minus lambda I will then turn into 1 minus lambda, 1, -3, and 2 minus lambda. So that's our key step there, that minus lambda I is just subtracting lambda on the main diagonal. After you get to that stage, we begin to row reduce, or excuse me, calculate the determinant. This will be equal to product of the main diagonal, 1 minus lambda, 2 minus lambda. It's a shame that there's no zeros here because it tells us that this is a factorization that's useless to us. We need to expand it out next. From here to here, the product is -3, but we flip the sign and get +3 altogether. Now we have to expand all this out. We're going to get 2 minus lambda minus 2 lambda plus lambda squared plus 3. This is kind of the fun part of the problem. It's now just college algebra, typical algebra stuff. We've got a lambda squared minus 3 lambda plus 5. Now, this is a interesting polynomial equation, right? In the variable lambda, it's of degree 2. But when I see a 5 here that's prime, I'm not seeing an easy way to factor this thing by trial and error. Instead, we're just going to use the quadratic formula, and that's what's going to give us our eigenvalues. This would be an awful question. I have to be completely honest. I don't like these questions in exam settings because throwing a quadratic formula at someone out of nowhere is just rude. You need some expectations that it's coming. This will happen in the homework questions, but not in an actual exam setting. So we're going to hit it with exactly, that's our discriminant. Yeah, we've got it. So we need to hit it with that. Good memory on that one. I usually get foggy if I haven't used that in, say, like 2 or 3 years. I forget just exactly how it goes. And when you're calculating these things, usually you want to do the discriminant first, instead of writing down the whole thing. So let's come over here and say, for our problem, b squared minus 4ac is going to be quantity -3 squared, minus 4 times a is a quantity 1, c is the quantity 5. So we get 9 minus 20 for a -11. And that tells us -11 is going inside the root. We're going to have 2 complex valued eigenvalues. That's definitely interesting, but you will always have eigenvalues. There's just no guarantee that they're going to be real valued. So in the next step, we can say equals 0. Now it's a characteristic equation. The solution to that is fully described in this way. So we will get lambda equals, taking the opposite of this sign for a +3, add or subtract the square root of -11, but the root of -11 is going to be I root 11 is how it would be typically written. So plus or minus I root 11 divide by just 2, since A is 1. So we've got it, folks. Those are our two complex valued eigenvalues. This tells us something about what the matrix is doing. This is going to be some kind of rotation in the plane and possibly a rescaling whenever you get complex eigenvalues. But any questions at all, folks, on the process of getting those eigenvalues?
Is it possible that the original mathematics, if we reduce it to the strong form, does it give us the same?
And actually, any kind of reduction that you do on the matrix will change the eigenvalues. It's really unfortunate. The only reduction you could do is right here, but look what would happen if we did try a reduction. Let's see here. If we try to eliminate the 1, oh boy, we would have to divide this by 1 minus lambda to make it a 1. Almost don't want to do it. You would have 1 minus lambda divided into here. The algebra gets really out of control. But the original matrix right here, we actually shouldn't row reduce it because any row reduction whatsoever will change eigenvalues most likely. That's unfortunate. And I think that was one of the comments in section 5.1. Row reduction cannot reveal eigenvalues. But other questions about that so far? I would say if you got here and spat out this, that's completely fine. Because I would consider all of this to be, although it's interesting algebra, it's not really the thrust of the course. It's Polyg algebra, not linear algebra. So anything that's kind of like that, yeah, you can just compute it off scratch, compute it with a calculator. I would be okay with that. What I'd be mostly looking for is the determinant, the equation expressed to that point, and then, yeah, if you go right here, I'm okay with that. Other questions so far? Okay, well, that's kind of an odd matrix. I felt like we had to do this one since I assigned a bunch of 2x2 matrices where all we're doing is finding the eigenvalues. But I think exactly one of those cases, let me think again. You might use quadratic formula in 2 of them, but I believe one of them did come out complex valued like this. So that's weird when it happens. Move on to the next one. We're practically done with this section, as weird as it sounds. This is a pretty short section. We're now getting into some interesting theorems, the ones we've been hinting at. This theorem tells us that the determinant of the matrix A is always equal to the product of the eigenvalues of A. That's the kind of work that we were hinting at. And because that's so important, let's take a tour of our results so far. In section 5.1, we were told that the eigenvalues of a triangular matrix are its entries on the main diagonal. So that's a wonderful theorem. And then we're also connecting that all the way back to section 3.1. Section 3.1 said, somewhere down here, there it is, theorem 2. If A is a triangular matrix or diagonal, then the determinant of A is the product of the entries on the main diagonal. So that's the determinant right there. But every one of those highlighted entries, those are also eigenvalues. So clearly, multiply the eigenvalues together, and you get the right determinant. So that's how those ideas connect back to this one. The determinant of the matrix is always the product of those eigenvalues. Well, any questions, folks, with that idea? The row reduction can change your determinant as well. Let me see if I have an example. Let's see. The thing that's tricky, though, is we often use this a lot. If we do row reduction right here, just right, and we do say this operation, then we're not really changing too much. We're going to maintain the determinant. So what did we do here? We took -2 times this row, added to the row below, and we got the right value out. But if we did something else to that, 213, now let's maintain the 0, 0, -5. And one thing you can do with this is multiply this row by anything you want. Let's multiply it by, say, 10. 60, -30, 40. When we do a cofactor expansion this way, it'll go positive, negative, positive, negative. We'll get a +5. Eliminate those. We have a 2, 1, 60, 30. And this is gonna turn into 5 times. Yeah, here to here, it's gonna be 60. Oh, thanks. That's what's gonna change the result here. Negative 60 minus 60. Thanks for spotting that. So we get negative, well, 5 by negative 120, which is gonna turn into, this is turning into a longer example than I thought. Let's keep going. 5 by 2 is 10, carry the 1. That's gonna look like negative 600, but we were expecting negative 60. So this one row operation right here of just multiplying a row did change the determinant, but that's because we didn't account for it using these properties here. So your question, Rajab, is a really good one because well, all this is telling us is you can use row reduction, but you need to be careful. And this is the only one that doesn't change the determinant, a row replacement operation. But does that make sense there? Gotcha. Once you did the row replacement operation right here, another wild thing that's happened is the eigenvalues of that matrix by the red dot are not necessarily the same as the eigenvalues over here to the left on the original matrix. So although we're not changing the determinant, this one is not guaranteed to have the same eigenvalues at all. It's kind of weird. So row reduction is awesome, but it's terrible when it kind of gets weird or fails. Yeah, go ahead.
Yeah, so sometimes you'll have, like, as we saw at the beginning, different, paths to the same end result when you're doing row reduction. And, would that get in the way of the potential right answer, so long as you're, sorry.
No worries. That's a lot of ideas that are floating around here.
I just mean, can you, as long as you're going for that, can you do row reduction in a way where you'll, end up with the wrong determinant there, or is that not related?
In this case, if you're using row reduction and you're only using part A, you would always get the right determinant. But yeah, if we did a row reduction of, say, divide this row by 2, but we didn't put a 1/2 in front, that's when we would start getting a different answer on the determinants. But when it comes to eigenvalues, it's even more touchy. Like, for example, we go down to this one right here, and what did we do to this? I think we took row 1, added it to row 2. So we did a row replacement operation on this thing, but it in fact did change the eigenvalue. This one turned into a -8. But let's take a look at these. Well, in either way, the determinant of this one was 0 because there is an entire, let's see here, 0 row, and the determinant of this one is still 0. The determinant didn't change. It's the eigenvalue that changed when we did the row replacement operation on this matrix right here. So again, that's kind of weird. Eigenvalues are more sensitive to row reduction. Essentially, if we want to find the eigenvalues of, oh, where did I go? Of these kinds of matrices, we have to leave them as is, they are right there. Other questions at the moment? Okay, well, we've got a nice theorem again. It's taking a bunch of ideas and throwing them together, determinants with eigenvalues. And this is getting us even closer to our end goal in chapter 5, diagonalization. Diagonalization is really just a way to factor your matrix. And that's a matrix factorization right there. We expect that's useful because most of our interesting results in algebra somehow involves factorization. So here's our core definition for getting into this. It says if A and B are both square matrices and of the same size, they're both n by n, we'll say that A is similar to B if there's an invertible matrix P for which you can write this equation. Sometimes people call this a kind of conjugation, P inverse AP, or you could write A is P times B times P inverse. Either way, you're dealing with a similarity transformation. And we're very interested in matrices that are similar because one thing that happens with similar matrices is their determinants should be the same. That's what example 3 is asking us to show. But if their determinant is the same, then their eigenvalues ought to be the same. Potentially, that'd be a harder proof. Let's take a look at this example 3 just to show how it goes. Reading a question like this, you'd first look at this part. Show that if A and B are similar, from right here, we should just write down exactly what it means for A and B to be similar. Let's say, since A is similar to B, we have A equals, I'll go with this equation right here, P times B times P inverse. And although it's kind of implied that P is an invertible matrix the moment we wrote that, it's not a bad idea just to say here, where P is invertible. So we want to show next, the determinant of A on the left must be exactly the same as the determinant of B on the right. How can we make that happen? We go to section 5. Or no, we don't go there. We go to section 3.2. And in section 3.2, let's see what we've got. Somewhere is a nice list of different properties of determinants. And here it is. It says if you're taking the product AB, the determinant of a product, you can factor that down to determinant A times determinant B. So we'll use that here. Even if there's 3 factors or 5 factors, it'll work the exact same way as it's exhibited right here. So next step, let's take determinant of A. The moment you took the determinant of A on the left side, we must do it on the right-hand side. So now it's determinant P, B, P inverse. And let's make that a little bit more readable. Now we're going to use that formula we just displayed. This will turn into determinant of P times determinant of B times, I wouldn't want to say determinant of P inverse. There's a better thing to put there. Anyone happen to know a good formula for inverse determinant? Good call, absolutely. If it's a P inverse, it goes in exactly as you said. That always looks kind of weird because you can't just take a matrix and put it in the denominator, but the determinant function is giving you a real number, so that's absolutely allowed. And then it allows a cancellation from here to here. We now have that it's equal to determinant to B. And that's all we were meant to show. We now have a long chain of equalities that connects determinant A to determinant B. And that means this whole proof right here has been supplied. Similar matrices preserve determinants, in other words. But we want more than that. If they preserve determinants, we hope that it preserves the eigenvalues. And it turns out that is also true. But any questions first, folks, for this example here? Okay, let's get to the bigger result. Theorem 4 says now, if you have similar matrices, let's just say what it means right here. This means A is going to be equal to B times P times P. Oh, let me try again. I got these out of order. A is going to be equal to P times B times P inverse. So that's what it means for similarity. Then they have the same characteristic equation, and they will have the same eigenvalues. So our work on determinants extends down to this statement. We're now really keenly interested in similarity because we've been fighting with something all along in chapter 5. The fight is you cannot row reduce that to get the right eigenvalues. That's unfortunate. But what you can do is if you find a matrix it's similar to, that's the concept you want. Similar matrices will preserve the eigenvalues. Row reduction does not. So that's the big punchline with this idea here. We like similar matrices only because of that fact. So this is a really short example, but it's could be a really fast concept question, potentially on the final exam. It says, let A be this mess of a matrix. B is interesting because it's a diagonal one. All the entries are on the main diagonal. And this is our P matrix right here. It goes on to say, then it can be shown A is equal to P times B times P inverse. That's a bold statement because what it was really saying is that A is similar to B. Let's say this right here. Since A equals P times B times P inverse, it follows that A is similar to B. So we have a similarity transformation the moment they said this is true. We don't want to check it out because that could take a little bit of work, but I did throw it into a computer program. It really does work out this way. The matrix A factors in this weird way, P times B times P inverse. And this is definitely an invertible matrix. Well, they say use this fact to compute the eigenvalues of A. Well, we'll use this idea. The moment you said two matrices are similar, then they will have the same eigenvalues. A is similar to B, and this is our B matrix. So we can now say the eigenvalues of A are, we get to read them right up here. This is upper triangular, lower triangular, all at once. We just call it a diagonal matrix. That means the eigenvalues were just staring at us this whole time. There, and there. But because A is equal to P, B, P inverse, the eigenvalues of A are the eigenvalues of B. So that's the one concept that we do have for eigenvalues. We can say lambda 1, 18, lambda 2 is 12, and lambda 3 is 6. And we did it, folks. That's a really fast way to compute eigenvalues, but it only works in these kinds of contexts. Row reduction is always going to fail when it comes to finding eigenvalues, sadly. Any questions at all, folks, with the conclusions here? Okay, there's even more that you might be able to say. This matrix was special, and so was the similarity transformation, because B is diagonal. It means this similarity transformation did not just reveal the eigenvalues, it reveals even more. Those are the associated eigenvectors in the system. The question wasn't asking about it, but you know what? That's an important enough preview. Let's put it here in pencil to make it unofficial. Those are the eigenvalues, and they have associated eigenvectors. V1, 140. Let me double check that's readable. Okay, it's kind of hard to see on my screen over here. V2, corresponding to lambda 2, is 111. And V3, corresponding to lambda 3, is 031. So if you know you have a similar matrix, you know just about everything with the total eigensystem. You know all eigenvalues and associated eigenvectors all at once. So these are nice matrices when you can diagonalize them, but when you can't diagonalize your matrix, that's when we call it defective, and that's what we're looking for. This would be impossible if, in this problem, we found an eigenvalue of multiplicity 2, but the associated eigenvector had dimension 1. If that happens, there is no diagonalization. You have a defective matrix. But when it works, this is fantastic, and there's tons of applications to diagonalization. Well, we did it, folks. That's the end of these notes, section 5.2. Any questions before we take a look at 5.3? Okay, well, keep those thoughts in the back of your mind. We're going to take a look at diagonalization right away. I think chapter 5 is kind of weird in this book because 5.2, 5.3, I think a lot of folks would have just put them together, but it's okay if we take a little bit more time and have a little bit more granularity in looking in these ideas. So in section 5.3, we're going to start by looking at another similarity transformation. By similarity transformation, we mean this matrix A can be factored as P times D times P inverse. Here's the matrix P. We haven't calculated P inverse, but we are given the matrix D. And the whole goal in this problem is to compute A to the power of 10. Ordinarily, that'd be a lot of work. If you want to compute A to the power of 10, well, your first thought might be, we have to find A, right? Which means you need to multiply P against D. You need to find the matrix inverse to P, put it in there, Multiply all those results together just to get your A. But there's another way you can go. If A is equal to P times D times P inverse, then one thing a similarity transformation will give us is a really, really fast way to calculate powers. So for example, A squared, if we try to break this down, it factors as A times A. But A is P times D times P inverse. So we get to write that twice. P times D times P inverse. My parentheses I put in are just for showing the substitution of changing A into its similarity transformation. So you could drop parentheses, reassociate if you wanted to. But at this point in the course, you probably just want to do this. P times P inverse turns into the identity matrix. The identity matrix just falls out through multiplication. What you're left is P times D times D. So you're looking at P times D squared times P inverse. So that's what A squared comes out as. And already you probably spotted a pattern, right? If it's A power 2, you expect power 2 here. Let's show it holds for power 3. We're not going to do a proof by induction to really prove it. We're just going to show it's plausible. So don't expect you have to do proof by induction. So for A cubed, what I would do is go A squared times A. Because we already calculated A squared, it's P times D squared times P inverse. Next, substitute in the value from A for the line one, P, D, P inverse. Now it probably just looks like deja vu. Here's P and P inverse canceling. You'll write out your answer as P. Here it's D squared times D, so we're up to D power 3, times P inverse. So that's what A cubed looked like. And at this stage, I think we're all probably convinced that A to the power of 10 should be equal to P times D to the power of 10 times P inverse. That look right to folks for that conclusion there? Awesome. So now what it boils down to is, if you want to calculate A to the power of 10, well, we're going to need to potentially put in P, multiply against D to the power of 10, invert P and multiply against P inverse. But before we go into all that work, which sounds like a lot of trudging through this, let's just take a look at D to the power 10. So we're back to this matrix. If we do D squared, here's what it would look like. 1, 0, 0, negative 1, multiplying 1, 0, 0, negative 1, and here's the end answer. I'm going to write this down in a kind of a funky way because it's more about the pattern than the actual end numerical value. So the matrix multiplication will be taking 1 times 1. So I'll write that in as a 1 squared, even though we clearly know that's a 1. For row 2, we'll get 0 times 0. So 0 merges down below. Now we're done with this row. We move over to that column and do the same thing. 1 times 0 for 0, 0 times negative 1 for 0, so 0 in total. Next will be 0 times 0 for 0, plus negative 1 times negative 1. So I'll write this one as a negative 1 squared. So notice what's happened. If your matrix is diagonal and you multiply it against itself, what seems to happen is you're just taking the diagonal entries and squaring them. There's a pattern there as well, but let's show it one more time just to see if it's holding up. D cubed. Well, you could break that up as D times D squared. First, I'll substitute in the matrix D, 1, 0, 0, negative 1. Next, we'll throw in D squared, which we calculated to be 1 squared, 0, 0, negative 1 squared. And now if we do the same multiplication, we will get this as a result. So first, we're using this column here. It'll be 1 times 1 squared, so 1 cubed, plus 0. Next, we'll get 0 times 1 squared for a 0, negative 1 times 0 for a 0 as well. And yeah, it looks like entries really are constrained on the main diagonal. But let's do it again just to be careful. We have 1 times 0 for 0, then 0 times the negative 1 squared, still 0, for a total of 0. Then it's going to be 0 times 0, -1 times -1 squared for -1 cubed. And this really does look like a pattern. It turns out, let me see if I can scroll just a bit, that d to the power of 10 really just boils down to take your diagonal entries, raise them to a power 10, and because that's what we really were after, let's just calculate these entries right here. 1 to the power of 10 is definitely a 1. 0, 0, -1 to the power 10 is a 1. It turns into the identity matrix right at that stage. And so now we're nearly done. Here's our end answer. A to the power of 10 is a matrix P times d to the power of 10 times P inverse. But we see that d to the power of 10, that's a glorified identity matrix. So let's throw that in just to connect the dots. That's P times I times P inverse, which means it's P times P inverse. And well, that means the end result is the 2 by 2 identity matrix again. So that's all A power 10 would come out as. Seems like a lot of work for just about nothing, but hey, we got an answer. That's the important thing. Any questions, folks, on getting to that stage? Okay, so this is one of the nice uses of matrix diagonalization. This is sometimes done in computation where you have a dynamical system that changes by doing a matrix multiplication. Maybe you're modeling the populations of something like predator-prey systems using discrete systems. Every time you multiply by the matrix A, you're updating a season, looking at the new populations. And so calculating A to a high power is a common problem, but it could become unstable in your systems if there's numerical problems. Yet diagonalize your matrix and the computations numerically become extremely stable now, since it just boils down to figuring out this as a power. So that's one use of matrix diagonalization. So now that we have a concept of it, here's the definition. Well, let's see if we can make it seem less bad. Let's start off with the definition here. It says a square matrix A is diagonalizable. That's a heck of a word. I'm not sure if it's even a real word, but that's what mathematicians do, that just throw that, use that enough and it'll end up in the dictionary. In fact, this has ended up in the dictionary, which was just a mathematical shorthand for if and only if. But we'll say a matrix A is diagonalizable if it is similar to a diagonal matrix. So in other words, diagonalizable means A looks like this, just like we were working with above, where P has to be invertible and D is diagonalizable. Now, because it's a diagonal matrix, I think using green color coding makes sense. In all of chapter 5, green is trying to emphasize we're dealing with eigenvalues, and blue is trying to emphasize we're dealing with eigenvectors. So just like we did in the last section, this matrix contains all of the eigenvalues just because it was similar. But because we're similar to a diagonal matrix, we have even more going on. So that's what Theorem 5 is all about. The heck of a theorem, so let's take a look at this carefully. The first statement is important, but it's not descriptive enough. It starts off by saying an n by n matrix A is diagonalizable if and only if you have n linearly independent eigenvectors. So if you have enough independent eigenvectors, you can diagonalize. But I think this is the fact that we usually use more often when thinking about diagonalization. We'll say that A equals PD P inverse, meaning you have it diagonalize it with a diagonal matrix D, if and only if the columns of P are your n linearly independent eigenvectors. The diagonal entries will be the eigenvalues that correspond to those eigenvectors, just like we did in the last notes. And so this is how we diagonalize a matrix A. We just need enough linearly independent eigenvectors. And if we can't find them, if there's less than n linearly independent eigenvectors, that's when we go ahead and say the matrix A is defective. Well, any questions, folks, with that definition there? Okay, well, down below, we've kind of done this problem, but it's a good idea to do it again while we're looking at Theorem 5. We'd see what happens to A. I don't even know what A is. We'd have to compute this, but it's been given a similarity transformation where we have a matrix P here, those columns 1, columns 2, and columns 3 all match up. Only difference is the inverse right here. So we have a matrix P going this way. It's this one and this one. This is our diagonal matrix D, but I think it's a good idea to just emphasize the main diagonal. The question is, what are the eigenvalues and corresponding eigenvectors of A? And for each eigenvalue, state its multiplicity as well as the dimension of the corresponding eigenspace. That's a lot of words, but here's all they're asking us to do. We can say that since A is diagonalizable, with A equals P, D, P inverse, where P equals 1, 1, -3, 0, 1, 0, 2, 0, 1, and the diagonal matrix D is 5, 0, 0, 0, 5, 0, 0, 0, -2. All we have to do is just summarize what we see here. So the theorem above says the diagonal entries on your matrix D are the eigenvalues of A. So we can now say lambda 1 is 5, lambda 2 equals -2. So we stated the eigenvalues, but we also want the corresponding eigenvectors. But it also says for each eigenvalue, state its multiplicity. Let's say that right here. For lambda 1 equals 5, this has multiplicity 2 only because it appeared twice on the main diagonal. So multiplicity 2. This one showed up once, so this one will have algebraic multiplicity 1. Next, let's get the corresponding eigenvectors of A. Now we have to be kind of careful. If we're talking about lambda 1 equals 5, and it shows up in columns 1, columns 2, the corresponding eigenvectors would be columns 1, columns 2 as well. So we'll say here, V1 equals 1, 1, -3, and V2 equals 0, 1, 0 corresponds to lambda 1. It wants to know the dimension of the corresponding eigenspace. So let's say eigenspace has, well, if there's two eigenvectors, these are guaranteed P to be linearly independent. We'll say dimension 2. So that's a lot of paraphrasing there. Any questions, folks, on how we tied down these ideas here so far? Okay, now let's just do it again. For the other eigenvalue, -2, its corresponding eigenvector is 2, 0, 1, only because that one's in column 3, and that's where we pulled that eigenvalue. So we'll say V3 equals 2, 0, 1 corresponds to lambda 3, and its eigenspace has dimension equals to 1, only because we found only one eigenvector there, this one here. Well, so far, we haven't done a lot with diagonalization. All we've really been looking at is when you see the diagonalization, what are the eigenvalues, eigenvectors? That's been the punchline so far. But what we'll do going forward is we want to diagonalize. We'll show what the methods actually look like to take a matrix like this one and actually diagonalize it. They're not all going to be diagonalizable, so we're going to be on the lookout when the matrix is defective. In other words, it's not possible to diagonalize it. That will happen whenever you see a high multiplicity that produces a dimension less than 2. That will automatically imply you have a defective matrix. Any questions at the moment before we launch into this one? Okay, we've got about 15 minutes. I think this will be a wise problem to be the last one for the night. So let's give this one a try and see how it goes. Then when we come back a week away from today, after exam 2, we'll look into more diagonalization kind of problems in different contexts. So let's give this one a try first. Makes sense to try a 2 by 2. And if you're going to diagonalize a matrix, your hope of hopes is it looks like this one. This one's lower triangular, which means you can just find the eigenvalues by visual inspection. It's 2, 4, 2. This one's not, and row reduction isn't going to get it there. So we have to start this problem by taking, in step 1, determinant A minus lambda I. Ever since section 5.1, that little expression there just keeps on coming back. So over here on the matrix, go 2 minus lambda, a 2, then a -3, and a -5 minus a lambda. So we're dealing with this determinant here. We'll just crank it out by brute force. There's usually no reason to try to do any row reduction within the determinant. It usually makes your work more complicated. So take the product of the main diagonal, 2 minus lambda, multiplies -5 minus lambda, then subtract the product of the off diagonal, which is a -6, so +6 altogether. Now we're back in the land of just crank this out through algebra, so let's work this one out. -10 minus 2 lambda plus 5 lambda plus lambda squared plus 6 altogether. Let me know if something looks weird algebraically. Sometimes when you do the simpler problems, that's when your brain kind of gets a little bit less focused, and that's when I make mistakes. So I've got a lambda squared plus 3 lambda minus 4. No quadratic formula on this one. This one looks very factorizable. Let's go lambda lambda. This was a real final exam problem. I try to arrange for this sort of setup where it's going to factor fast. Since I don't want to make the exam about college algebra, we just move on through this step really rapidly. Looks like we're going to need a +4 minus 3, or excuse me, let me try again, -1 to get to the +3. These multiply to -4, add to 3. So we've got a good factorization. We set it to 0 and conclude the eigenvalues are lambda 1 equals -4 and lambda 2 equals +1. So that's our first step, find all the eigenvalues. Now these have the same multiplicities, they're both multiplicity 1. But the moment you find a high multiplicity, that's the first eigenspace you want to look for. Say for example, if this had multiplicity 2, I would look at the eigenspace of that first, because if I have dimension 1 on that eigenspace, automatically diagonalization is not possible. So you want to look to the places where it will fail first, so you don't do a bunch of unnecessary work. We'll re-explain that on this one. This one has eigenvalue lambda 1 equals 2, multiplicity 2. So you want to look at the eigenspace on that one immediately before anything else. But we're in this land right here, so let's keep on working through it. After finding the eigenvalues, we'll have 2 additional steps. If there was 5 eigenvalues, I'd say 5 additional steps. That's kind of an unfortunate statement. But here's step 2. We focus again on lambda 1 equals -4. And now we need to find its associated eigenvector. So solve A minus lambda I, x set to the 0 vector. In this case, it'll be A plus 4i, x set to the 0 vector. We need to find the total solution to this system. So back over here, we're adding 4 to the main diagonal. And it seems silly, but this is actually pretty important. I usually make a mistake where I forget the sign flip. It's -4 here. You're not subtracting 4, you're adding 4 to the main diagonal. So the augmented matrix is going to be 6, 2, -3, -1, 0, 0. Immediately just jump right into row reduction. This goes pretty fast. And I wouldn't do anything too fancy. Let's divide row 1 by 6. We will get a 1 -3/6 or -1/2, 0, and then it's going to be 2, -1, 0, and row reduce. Now, I can guarantee you that this row is 0. Why? Well, that's a real eigenvalue. That means this matrix equation has to have a free variable, or else we made a mistake somewhere. So I'm going to put in 1, -1/2, 0, but I would still check it out, because if I don't get our zeroed out row, then there's possibly a mistake up here. We have to investigate. So multiply row 1 by -2, add it to the entries below, and we'll get 0. This multiplied by -2 is a +1, add below is 0. We're on the right track the moment we see those zeros. And now we can say that's x1, x2. And this implies x1 is +1/2, x2, x2 equals x2. That's our parameter or free variable here. And we can let it be anything we would like. A lot of people would set x2 equals to 1, and that's totally fine. But if you did that, and you looked in the back of the book, you might be confused. They probably won't use that. Here's something that's weird. This matrix is diagonalizable, but there are infinitely many different ways to diagonalize this. It's all up to what choice you make right here for x2. So lots of right answers. And in this problem, I would set x2 equals to 2, only because it's typical you'd want to clear the fractions right here. So when x2 is 2, this implies I want to write this as a pair. Lambda1 is -4, and its associated eigenvector v1 would be equal to 2 there would give us a +1, and down below a +2. So we did it, folks. We have an eigenvector corresponding to the eigenvalue -4, and that was so fun. We will do it again because there's another eigenvalue we have to produce an eigenvector for. Any questions on this step, however? Okay, essentially this is section 5.1, 5.2 all put together. So now in step 3, we just do it all over again. I'm going to need the original matrix A, so let me just grab it for the moment. Our next eigenvalue is a +1. So this time it means we're going to solve. It's always a minus lambda I, but we're throwing a 1 right there. So it's going to be a minus 1 times I times x set equal to the 0 vector. So that's our equation to solve. It's always really fast. Now we're going over here, subtracting 1 from the main diagonal. The augmented matrix will be now a 1, 2, -3, -6, and 0, 0. This one's even faster to row reduce. We have a 1, -3, 0. Multiply row 1 by -2. Add to the entries below, and we just get 0, 0, 0. So let me throw in this just as a reminder. This now implies x1 is 3x2. x2 is free variable, so it's set equal to x2. And now, just like before, we have to do the uncomfortable work of pick a value for x2. Usually you pick a 1, but it's typical if there's a fraction, you'd pick the value to clear the fraction. Here, let's just set x1 equals 1. Then here's our conclusion. For lambda1 equals -4, the associated eigenvector is, oh, hang on, let me try again. I think I grabbed from up here. I should have grabbed from right here. Lambda2 equals +1. Let's just start that whole line over. So for the eigenpair where lambda2 equals 1, we found the associated eigenvector is v2 equals 3, 1. So we're just about there, folks. Here's the final step, step 4. Step 4 is just a summary. Let's express that by saying diagonalize A. Here's how it goes. We'll write A is equal to a matrix P. And let's color code this as we go. So here's the P matrix that comes in first. Next, it's the diagonal matrix. And then the matrix P comes in again, but don't forget to write this in. This is important. We have to put the inverse there. Now, next thing I would do is throw in the eigenvalues. This is interesting because you can put them in any order. Usually you'd go in order of what you wrote down on paper. That's natural. But you could have put -4 here and it works out as long as vector 1, 2 goes into the second column right here. So if you put -4 here, then you are now forced to take V1 and drop it into column 1 in 2 places, both here and here. So that's how the pattern goes. Next, you'll take your other eigenvalue, lambda1 equals 2, go 0, 1, take your eigenvector 3, 1. It is forced now to be in column 2 for both matrices. So it'll go 3, 1, 3, 1. And right here, I do have a big comment to make, but this is where the problem would end. But any questions, folks, to this stage?
-4 in the second column.
It is possible, absolutely. So let's actually write our answer this way, just to emphasize it is absolutely possible and gives you still the correct diagonalization. So if we go 0, 1, 0, -4, oh, let me try again. That's not diagonal at all. One more try. 1, 0, then 0, -4. Then what I would do in this case is 3, 1 now has to be in column 1. It'll be here and here. 1, 2 has to be in column 2. So it'll go 1, 2, 1, 2. It's kind of amazing in a way that you can put these in any order, but as long as you're consistent with the eigenvalue, eigenvector pair, you get the right diagonalization. Now, here's my big comment I did want to make. Both on homework and on exams, you do not need to calculate that inverse. You can if you want, but you're doing a lot of additional work if you decide to do that. I'd say if you want to calculate the inverse there, do it for the purpose of homework, but skip it on the exam. I might have a specific question for matrix inversion. Usually we just leave our answer right in this format. So you do not need to find this inverse. So in other words, your answer is just fine the right as it looks, just like that. The only reason you might want to find the inverse is if you're multiplying all together to make sure you really got back this matrix. But the check is just as long as the problem sometimes, especially for a 3x3 system. This is a fine stopping point for these kind of problems. Well, any questions at all, folks, with getting through that diagonalization process? Okay, it is quite a process. You'll notice this is a long problem. And so when we go to the final exam, it's not necessarily going to be 20 questions. It'll involve problems like these where we have a little bit of extra steps to take. So I'm probably going to be anywhere around 14 to 18 questions. If I'm on the 18 question ends, that means I put in a lot of small concept questions. If I'm on the 14 question end, then that means maybe the diagonalization was longer or something like that. But also on the Moodle website, it's a good idea to talk about it. We're getting close to the final exam. We'll be posting additional problems here. I'll be posting old final exams from semesters past, so you'll know about what you're getting into. It is a big change to go from the 75-minute 20 questions exams to a final exam. So I want to give you a heads up of what it really looks like so you can prepare for it. But I think this is a good stopping point for us today, folks. Any last questions before we call it a night?
I know you can cover from first to the end of.
Yeah, it'll be a comprehensive exam. And one thing I did want to mention is, as a comprehensive exam, sometimes people put way more emphasis on these kinds of sections that were not on exams 1, 2, or 3. I'm not going to do that. I'm just going to make it fully comprehensive, so there won't be any emphasis in one section or the other. I'm just going to take a selection of topics from the whole course. No one spot for emphasis. Other questions about that at the moment? Okay, well, have a great weekend, folks. If you have questions while you're studying, I'll be available and happy to help. You bet. Have a great one. And here's these for you, Scott.
So just in general, answer the same kind of questions we got previously, that should be okay for the final.
Yeah, absolutely.
Okay.
You can make sure that's.
All right, yeah, but just the non-raised to do review would be there then, or.
Yeah, I would highly encourage, take a look at my new exams. In fact, when I go to books and materials, that is when I know when you like, I'll like blend down exams, as an audition. And I'll also be posting that on exams as well.
Thank you.
Yep, you betcha. That was a lot easier. If you do that, we can go and like for daily.